Every read your service sends to disk that comes back empty is money you spent on nothing. You paid for the seek, you paid for the wait, and your users paid in hours of their own patience spread thin across a year of those reads. On a busy system, most of your lookups are misses, and the misses are the expensive answers, not the hits. So what would you give for a way to know, without touching the disk at all, that the thing you were about to go looking for was never stored at all? That question is old, and the man who answered it had worse hardware than you will ever complain about. In 1970, a computer scientist named Burton Bloom was working on hyphenation, of all things. 9 words in 10 could be broken correctly by a handful of cheap rules. The stubborn 1 in 10 needed a dictionary, and the dictionary was far too large for the memory of the day, so every stubborn word cost a trip to spinning storage while the machine sat there doing nothing at all. Park that ratio of 9 to 1, since it decides everything later. You have inherited his exact arithmetic and you probably pay it without ever having measured it. Your cache is asked for keys it has never held. Your storage engine is asked for rows that were never written. Your fraud check is asked about accounts nobody has ever seen. Each of those wasted questions costs you a disk trip or a network round trip you did not need to make, and your users feel every one of them. How many of your lookups actually find something? Have you ever counted? State the problem plainly and it sounds impossible. You want a guard that sits in memory, cheap enough that you barely notice what it costs you, that can tell you a key was never added and be right every single time it says so. Not usually right. Right always, with no exceptions, while still being small enough to hold 100 million keys in the space your logging library wastes on a slow afternoon. The thing that does this is called a Bloom filter, and the whole of it is a long row of bits that start out at 0. Alongside the bits you keep a small number of hash functions, each one turning whatever key you handed into a position in that row. To add a key you run it through every hash function and you turn on the bit at every position that comes back. That is the entire write path. Nothing else is recorded anywhere. To ask whether a key was added you run the same hash functions and read the same positions. If any one of those bits is still off, the answer is no, and the term for that is a definite no rather than a probable one. That bit would have been turned on when the key was added, and bits here are never turned back off, so an off bit is proof of absence. If every position is on, the answer is maybe. Only maybe. Notice how lopsided that pair of answers is. Which means the structure has exactly one way of being wrong. It can tell you maybe about a key that was never added, and that mistake is called a false positive. It can never tell you no about a key that was added, so there are no false negatives at all, and that is not a tuning achievement or a lucky property of good hash functions. It falls out of the way those bits behave. What becomes possible when one of your two errors is structurally impossible? There is a second lopsided thing here, and it is the part that surprises people who thought they understood it. The filter never keeps your keys. It keeps a row of bits that some keys once touched. You have no way to list what is inside, no way to read a key back out, and no way to hand the filter to somebody as a record of what you stored, since every trace of the original key was thrown away the moment its bits went on. Note, the jargon around this is a lot of words for a very plain object. Membership query structure, approximate set, probabilistic data structure, and space-efficient summary all name the same row of switches with some hashes pointed at it. Bloom himself called his paper spacetime trade-offs in hash coding with allowable errors, which is the most honest title in the field, since it puts the word errors right there where a marketing team would have hidden it. Does knowing the fancy term help you size one? Not in the slightest. So how much does that guard actually cost you? Here is where the numbers get lovely, because the answer is a rule of thumb you can hold in your head. 10 bits per key buys you a false positive rate of about 1%. Not 10 bits per byte of key. 10 bits per key, full stop. 100 million keys at 10 bits each is 125 megabytes, and it will answer your question wrongly about one time in 100 and never wrongly the other way. Walk one key through the whole thing and the arithmetic stops being somebody else's rule of thumb. Take a row of 80 million bits, which is 10 megabytes, and 8 million keys already inserted at 7 positions each. That is 56 million bit settings landing in 80 million slots, and because plenty of them collide, roughly half of your bits end up on. Now ask about a key that was never added. Each of its 7 positions has about a 1 in 2 chance of being on already, so the chance that all 7 are on at once is 1/2 multiplied by itself 7 times, which is about 1 in 128. There is your 1%, and notice that you just derived it instead of trusting a table. What happens if you change 7 positions to 10? The same multiplication hands you about 1 in 1,000. Which is why the sizing conversation is short once you have that multiplication in your hands. So how do you size one? Not by feel. You pick the false positive rate your caller can actually tolerate, then you read off the bits per key it demands, and then you check whether that many bits fit in the memory you were willing to spend. 3 numbers, in that order, and the last one is the only negotiation. Now push on that number, since the shape of the curve matters more than any single point on it. Roughly every 5 extra bits per key divides your error rate by 10, because each new bit halves the chance that a stray key finds all of its positions already on. 15 bits gets you about 0.1%, and then 20 bits gets you about 1/100th. So the cost of certainty grows like the logarithm of the precision you are demanding, which is the friendliest growth curve in all of engineering. Doubling your memory does far better than having your error. Case in point, first compare that against holding the keys themselves. 100 million email addresses at 20 bytes each is 2 gigabytes before your hash table is added a single pointer of overhead, and in a real hash set you should expect to pay closer to 3 because of the load factor you have to leave empty. So just keep the keys, then. But that is not a plan you can put on every machine you own. So the filter is doing the same job for 1/16 of the memory. Which of those two do you want resident on every one of your machines? Notice what did not appear in that comparison. The length of the key never entered the arithmetic at all. An 8-character username and a 400-character URL with a tracking query string on the end both cost you the same 10 bits, because both get hashed down to the same handful of positions. That is genuinely perverse when you sit with it. The larger and more unwieldy your keys are, the better this trade looks, and I love that it works backwards from every intuition you have about storage. The number of hash functions is the knob people reach for, and it is not a more is better dial. Add hash functions in each key, then turns on more bits, so a full array of mostly on bits starts answering maybe to everything you ask it, because you have run out of off bits to prove anything with. Use too few and you are wasting a row of bits that sits mostly empty. The optimum sits near the natural logarithm of 2 multiplied by your bits per key, which for 10 bits per key lands around 7 hash functions. Would you have guessed 7, or would you have guessed 3? Note, you never have to write 7 independent hash functions, and this is the step where implementations get pleasingly cheap. One good hash gives you 64 bits of output, which you can slice into 2 32-bit halves and then combine them to manufacture as many positions as you want. So the cost per lookup is 1 hash and a few additions, and none of it touches more than a page or 2 of your bit array. Real systems live on this. RocksDB and LevelDB keep a filter alongside every sorted table file and consult it first, because the default there is exactly the 10 bits per key from the rule of thumb above. Cassandra keeps 1 per table file too, sized from a false positive chance you set yourself. Google described the same trick in the big table paper as a way of avoiding disk seeks for rows that were never there. Squid used filters as cache digests so one proxy could summarize its contents for another without shipping the index. Case in point, content networks use them for something more interesting than lookups. Akamai reported that most of the objects they were asked for were requested exactly once, ever, and caching a one-hit wonder is pure waste, since you pay to store something nobody will ask for again. So you put a filter in front of admission and then only cache an object on its second request, because the first request tells you nothing about whether a second will ever come. The filter is the cheapest possible memory of having seen something before. Do not take my word for any of this, since the whole point of a rate you can compute is that you can go and check it. First take 10 million keys you know are absent, then ask your filter about all of them, and count how often it says maybe. That count divided by 10 million is your real false positive rate, and if it is not close to the rate you asked for, your hash functions or your sizing are lying to you. That measurement takes about 10 minutes and it settles the argument. Now the part that bites, and it bites in production rather than in a benchmark. You cannot delete anything. Turning a key's bits back off would turn off bits that other keys are also standing on, which would break the one promise the structure makes, so removal is not a missing feature that somebody will add later. It is structurally forbidden by the sharing that makes it small in the first place. The usual escape is to keep a small counter at every position instead of a single bit, so adding increments and removing decrements, and a position is only clear when its counter reaches 0. That is a counting filter, and the honest accounting is that 4-bit counters cost you 4 times the memory you came here to save. Is deletion worth quadrupling your footprint, or would you rather rebuild the filter on a schedule and keep the cheap version? That answer depends on your write pattern, not on anybody's blog post. In practice, the failure that catches teams out is not deletion, it is overfilling. You sized for 100 million keys and 2 years later you are inserting 400 million into the same array. Nothing errors and no alarm fires. The bits simply fill up and your 1% quietly becomes 40%, at which point your filter is answering maybe to everything and you are paying for a check that has stopped rejecting anything. Do you monitor the fill ratio of yours, or are you assuming the sizing you chose 2 years ago still holds? Caveat: there is a whole family of workloads where this structure is simply the wrong answer, and the received wisdom will not tell you so. A filter pays for itself when the negative answer is both common and expensive. If almost every key you ask about is genuinely present, you have added a hash and a memory read to every single request and rejected nothing, which makes you slower than the system you were trying to protect. If the underlying lookup is a cheap read from local memory, the filter costs more than the thing it guards. Where else does the idea run out? Newer relatives fixed the deletion problem properly. A cuckoo filter stores small fingerprints rather than bare bits and supports removal at a similar footprint, and quotient filters keep their data close together so they behave better in cache. And the unglamorous option deserves saying out loud: if all your keys fit in memory with room to spare, you cannot beat a plain hash set, exact, deletable, and easier to reason about at 3 in the morning. The honest answer is that most teams reach for a filter too early. There is no prize for probabilistic sophistication. The folklore around all of this is worth treating carefully, and I will admit the limit of my own confidence here. The 10 bits and 7 hashes numbers are near optimal for the classical construction under the assumption that your hash functions behave randomly, and real hash functions only approximate that. There is no guarantee that a rate measured on your colleague's key distribution transfers to yours, which is exactly why the 10-minute experiment above beats quoting a table at each other. Which brings us back to Bloom and his 9-to-1. He was not trying to be clever about data structures. He had a dictionary that did not fit, a disk that punished him for every question, and a job where being wrong one time in 100 meant a slightly odd hyphen rather than a wrong answer. That last condition you have to check for yourself, since his mathematics cannot do that one for you. So the two things worth checking in your own system this week are cheap to run and awkward to answer honestly. What fraction of your lookups are misses, measured rather than assumed, since under about half the filter buys you very little? And what does a false positive actually cost you in your own system, given that one extra disk read is a shrug and one wrongly skipped fraud check is a very different conversation? Get those two numbers and the decision makes itself. That part is your call rather than mine.